All right, so let's look at a secondary alcohol, because those are the ones that kind of give us the most trouble, the most variability. Because secondary ones can undergo SN1, SN2, E1, or E2, depending on the reagents we use with it. So if we don't want it to form a carbocation ever, we would use one of those 5 reagents I talked about before. So pick our favorite one. Let's do SOCl2 with a little bit of pyridine. So the first thing I would do for this is actually draw out SOCl2, because I probably won't do that for you, but you should do it. SOCl2, the sulfur is a really good electrophile, and so the lone pairs on the oxygen are going to attack it. And actually what happens is the electrons go up on the oxygen, number my carbons, of course. 1, 2, 3. 1, 2, 3. There's a plus charge on the oxygen here. So we've learned about this in lab, actually, about something called the Tetrahedral Intermediate. We talked about this about the Keck. This sulfur right here was sp2 hybridized, but now it's sp3, so now it's tetrahedral. But what happens with tetrahedral intermediates is that they collapse, and so these electrons come back down, and chlorine's a pretty good leaving group, right? So these electrons will go. So it looks similar to maybe your esterification protocol, maybe not. Never? No. Well, I have to check because I'll number. 1, 2, 3. So 3. Very good. Right? I lost Cl minus. Right. Okay, at this point, right? The pyridine comes into play. Make sure we know how to draw pyridine correctly. Pyridine's a base. It takes this proton, goes there. One, 2, 3. Cl minus is floating around. Pyridine took the proton. Now the Cl minus can do a backside attack, right? So this is that SN2 reaction, right? No carbocations are formed here. All those activation methods with SOCl2, PBr3, PCl3, zinc chloride, tosyl chloride, no carbocations. And there would be an inversion of stereochemistry, that's right. Just like we kind of saw in class. So these electrons actually, this is a little different. So the electrons go there, and all in one step, this chlorine leaves. Because one of the byproducts we make is SO2, which is a gas. Right, you can kind of see here's the SO2, S and the 2 oxygens. So that leaves. We also get Cl minus, and our final product, right, would be the substituted chloride. Right, but this goes through an SN2 mechanism. No carbocations. No carbocations. There's no carbocations. Can you have any rearrangements? No. So no rearrangements with these. So this is a nice thing. These are nice because you can use secondary alcohols and not get rearrangements. Whereas HI, HBr, and HCl, you still get rearrangements. Okay, let's look at one of our reagents we learned about, H2SO4, which we found instead of doing substitution, it does eliminations. But in this case, we have a primary alcohol. So let's see what happens to the primary alcohol. Again, we should draw out H2SO4. Number thy carbons. This beautiful day. 1, 2, 3. The alcohol, the OH, or the oxygen lone pairs attack the acid. they become protonated. So now we have water as a leaving group. All right. There you go. Right. Never mind carbons. But at this point, we have a choice to make. And this is the issue. We had a primary alcohol. Now we have a water leaving group on a primary carbon. So can we do an E1 mechanism here? No, we can't. So what do we have to do? We know it's going to be an elimination, right? We know we don't do substitution here. What are we going to do? Has to be E2, right? Has to be E2. Because how good of a nucleophile is this? It's bad. It's really stable, right?
Oh, yes, we said that in class.
Hey, thank you. Right? So what's it going to do? It's going to find, we draw our beta hydrogens in. Take that. Take that. So if we do E2, we still need what kind of conformation? So E2, we still need anti-periplanar, right? So don't forget that kind of stuff. So we're doing an E2 reaction, right? One step, no carbocation. So 1, 2, 3. Why couldn't it be what? Why couldn't it be what? Primary carbocation. Could we other form a primary carbocation?
Oh, no.
No. So it has to be E2. We know it has to be an elimination because it's H2SO4. So there's no good nucleophile. And it's a primary carbocation, so we know we can't do E1. So it has to be E2. Okay, so I have a pre-drawn problem here with a secondary alcohol. So let's talk about this. This is a secondary alcohol. Right? We have HBr. So if we have HBr, secondary alcohol, we should be thinking probably substitution, right? And probably what type of substitution? SN what? SN1. Yeah, SN12 is not an answer. Make sure. SN12? No. SN1 probably, right? So the first step is again, right, we're going to protonate our alcohol, make it a better leaving group. Get that proton. Get that proton. So I, of course, forgot to number my carbons. I'm not going to number the benzene ring. They're kind of there. Well, we don't worry about those right now. 3, 4, 5, 6. So we've numbered our carbons. We have our alcohol with a, now it's turned into a good leaving group of water. So we're saying 1, 2, 3, 4, 5, 6. So what's the next thing that's going to happen here?
The oxygen is going to break off.
Right, we're going to break the carbon-oxygen bond. We're going to form a carbocation. Right? Four, 3, 5, 6. Where's my plus charge at? Which carbon number? 2. Very good. All right, here we go. We've got a carbocation, a secondary carbocation. Now we have a choice. What do we want to do here? We could do a methyl shift. Let's do a methyl shift.
Oh, is there another option?
Oh, there might be. And the other option might be a better option. So we did a methyl shift, right? We're doing a methyl shift. We're going to move carbon 6 here over. Fine. One, 2, 3, 6, 4, and 5. Where should the plus charge be at? On 3. Very good. Okay. And then at this point, right, Br minus is, once it's finally satisfied, Br minus is going to attack, right? Then we get Br on carbon 3. All right, let's draw. That could be a possible product. Let's draw that up here.
Oh, there's 2.
Oh, this is the minor product.
That's the minor product?
Absolutely.
How dare you?
How dare I? How dare you? How dare thee?
Would we get this nice mark drawn?
Well, if he asked specifically for the major.
Well, now you know it. So the BR is there. This is 1, 2, 6, 3, 5, and 4. Right? You get it. What else could we have done? Which hydride? Which carbon? Carbon on 1, right? Now, why would we? So, is it a lateral shift?
Oh, no, it's that thing where it's right next to a benzene ring.
That's stupid. That is a stupid.
Wow.
Benzoic?
Benzoic. Isn't a benzoic more stable than anything else? Right? Benzoic, right, has all that resonance stabilization. Resonance stabilization is better than just hyperconjugation. Yep. So,
David Black is,
right, so we have a benzylic carbocation, which is more stable because of resonance. Resonance is more important than hyperconjugation. So the bromine's going to attack there. So the bromine's going to end up on carbon 1 in the final product. And that's going to be the major product. Resonance, benzylic, allylic, right? A benzylic is more stable than allylic, right? More resonance even. But allylic and benzylic are better than tertiary.